Hey everybody. Today we're doing a couple of examples using the negative binomial distribution and its special case, the geometric distribution. Here are the two problems we're going to tackle. As usual, I recommend pausing the video, trying these on your own before seeing my solutions. Number 1. Two evenly matched basketball teams play in a series where the first team with 4 series wins. Like, the NBA Finals or something. What's the probability that the series lasts exactly 6 games? What's the expected value of the number of games that will be needed? Let's let x represent the number of games needed for either one of the teams to win the 4 games. So here I'm just looking at one of the teams. Later on I'll double the probability that I find. Then x has a negative binomial distribution with parameters r equals 4, because you got to get 4 wins to win the series, and p equals 0.5. The teams are evenly matched, so you've got a 50% chance of winning each game. I've written the probability mass function of that negative binomial distribution here. Basically, you've got to get all but one of your wins in the first x minus 1 games. The series could last 4, 5, 6, or 7 games. That's r plus 1, r plus 2, and r plus 3. So we need to compute f of 6 in that probability mass function f of x. Plugging in, doing a little bit of arithmetic, we get 15.625%. That's the probability that one of the teams, like Team A, wins in exactly 6 games. If we double that, we get the probability that the series lasts exactly 6 games. It is exactly 31.25%. We can redo those calculations to find the probabilities that the series lasts exactly 4, 5, and 7 games to get this discrete probability distribution. For instance, the probability of a sweep, that is, one team wins all 4 of the first 4 games, is 12.5%. If you add up these 4 probabilities, you get 100%, just like you'd hope from a legitimate discrete probability distribution. We compute the expected value here in the usual way. We take each of the values of x, the number of games in this case, and multiply by their respective probabilities, then we add all those up. We get 5.8, so if you have evenly matched teams, the number of games needed to decide a 7-game series is expected to be just under 6 games. Problem 2. Cards are drawn at random with replacement from a standard deck until the ace of spades is drawn. Show that the probability of pulling it immediately after 100 failures is exactly the same as it was on the first try. These draws are done with replacement, so we have Bernoulli trials, and the number of tries needed to pull that one card, the ace of spades, has a geometric distribution with parameter p equals 1 over 52, because there's one ace of spades out of 52 cards. So, if x is the number of draws needed until that first success, then we need to show that the probability that x equals 101, given that x is greater than 100, is 1 in 52, which is the probability that the ace of spades is drawn on the very first try. So we're going to use the definition of conditional probability, which says that the probability of A given B is the probability of A and B over the probability of B. That's what's happening here on that first line that you're seeing. The second line is just noting that the probability of x equaling 101 and being greater than 100 is exactly just the probability that x is 101. The fact that x is greater than 100 here isn't adding any new information. The third line here is just using the probability mass function of the geometric distribution with parameter p equals 1 over 52. On the top part of that fraction, we have the probability that x is exactly 101, which is the situation where you have 100 failures, probability 51 over 52, followed by a single success, probability 1 over 52. The denominator there is just the probability of getting exactly 100 failures in a row, which is to say the probability that x is greater than 100. There's an immediate simplification. The 51 over 52 to the 100 is in the numerator and denominator, so that cancels. So overall, we get 1 over 52, which is exactly the same as the probability of drawing that ace of spades on the first draw. More generally, when x has a geometric distribution, the probability of waiting more than k trials for a success is the same regardless of how many failures have come before. A bit more mathematically, the probability that x is greater than j plus k, given that x is greater than j, is the same as the probability that x is greater than k. Here, j is the number of failures that have come before in the statement above. This is sometimes summarized by saying that the geometric distribution has no memory. A similar theorem can be stated and proved for the negative binomial distribution. So if you're looking to take this a step further, that's a good direction to go.